Okay, thank you very much for giving the opportunity to speak. So I have so my goal for this talk is to motivate motivate looking at symmetries in stochastic particle systems, and I'm going to stay here till the end of the program. So if you're interested in discussing that, you can always find me. So the TLDR, so the whole goal is to show is to kind of take Yang-Baxter equation and stochastic interacting particle systems and put them together and see what happens. And turns out that just simple graphical manipulations with the Yang-Baxter equation can give you some probabilistic consequences that are exercises at first, and then some non-trivial consequences in some limits. Okay, so because particle systems were not introduced yet at this workshop, let me do the hard job of discussing the history of how TASEP, Totally Asymmetric Simple Exclusion process, was introduced in biology. So imagine that you are getting a mRNA vaccine, like most of you did, and what happens in your cell is that there is this mRNA strand that looks like a line it looks like a discrete line, and at every location in this line, there is a certain letter, which one of the 4 letters encoding amino acids, and this line flies around, floats around in the soup inside the cell, and then ribosomes attach to this line, and they build proteins by reading these codes. And when you read the next letter, then from the soup of the surrounding, you attract the correct amino acid to build these protein chains. And this process can be modeled by a random system by saying that, well, my ribosomes are particles, and they definitely do an exclusion motion, so they can move right and left, but mostly they move in one direction, and they cannot overcome each other, so there is this exclusion rule. And however, there are lots of other things lots of other parameters you can introduce, namely, the speed with which a ribosome is moving is going to depend on what you see on the mRNA. And also, a ribosome can randomly detach, or maybe some other ribosomes can randomly attach. They can change their internal type, and the speed of motion might depend on this internal type. So there are lots of parameters that integrability doesn't know how to handle that. So, scrap that, and let's go to mathematics, and take a simplest possible model when you take a one-dimensional line, and you model each ribosome by a particle that can only occupy one site. Particles move only in one direction, according to independent clocks. So initially, maybe let's attach a coin to each particle and then flip them independently, and then each particle gets a heads or a tails, and then if it's a heads, then a particle wants to move one step forward in discrete time. But if the destination is occupied, then you don't allow the motion, and the update propagates from right to left, so there are finitely many particles. First one doesn't have any obstacles, so it moves like a simple random walk. Then the next one sees what happens, what did the first particle move or not, and then it decides to move. And then you get the next configuration, and you run this dynamics. This is called TASEP with discrete time, Bernoulli jumps, sequential update. And so the speed, meaning the coin flipping the heads probability of each coin, will depend on many things. It might depend on the location of the particle. It might depend on the type of the particle. It might randomly change. That is hard. So the most general solvable case is when you put particle speeds that depend only on the particle and don't change in the course of the dynamics. That's what I'm going to do. So I like putting as many parameters as I can into the model, and well, provided that the result is still integrable. So here is and then in that setting you get lots of symmetries that you can observe, and then these symmetries will tell you will tell you that your system is nice, and it will lead to interesting facts about the system. So let's say we're talking about just two particles. So suppose that I have a fast particle and a slow particle, and I consider two systems. If depending on whether I put the slow particle in front or the fast particle in front. So the fast particle is in front, then you take a Ferrari and a tractor, and the Ferrari quickly overcomes the tractor and doesn't even bother looking back. And so you have this type of dynamics. Maybe initially they interact a little bit, but then they diverge and never interact again. And they after this moment it's a random moment, but after that they evolve as simple random walks. On the second motion, when you put a tractor in front, they will interact a lot, and probably a lot of honking will be involved. So there are these two different systems, but now I claim there is a relation between them. So first relation is that, well, if you look at the particle in the back, then of course the long time speed, the slope of the second trajectory in both systems is the same, right? But surprisingly, it turns out that not only the slope, but the whole trajectory is the same in distribution. So if I erase the first trajectory, then you cannot distinguish the difference. There is a condition that the particles must start as immediate neighbors. If they start as immediate neighbors, then the second trajectory is completely the same. Okay? So why is it so? Well, you can get it from symmetric functions and Robinson-Shestley-Knuth correspondence by encoding, basically RSK in this simple example encodes unused jumps. So if here there are lots of unused jumps, here there are only a few unused jumps, and if you encode them correctly, you can actually match the two systems together such that the second trajectory doesn't change. But why is this symmetry nice? Is that, well,
isn't this the Berg property?
There is a Berg property. You can also derive that from the Berg property, I guess. Anyway, it's an exercise for whatever tools you know, try to prove that. So why symmetry is nice? Yes?
I didn't catch the basic statement here.
So you take two systems and erase the first trajectory, then the second trajectory, the trajectory of the car behind, is indistinguishable in distribution. It has the same distribution. Okay. So,
and in the second case with the tractor, is it the same distribution as
the blue thing?
One and X2 have the same distribution or not?
The first one?
No, on the right hand panel.
The blue. No. The first is a simple random walk of a slower speed. And the second one, the blue distribution, the blue curve here and the yellow curve here are the same in distribution. But
yes.
Here the yellow curve on the right is a simple random walk of a slower speed.
So the brown is the same on both sides in this.
No. I don't know. These are slow and fast cars.
Well,
so color encodes the speed.
X1 does not see X2.
X1 doesn't see X2. X2 sees X1 here. X2 does see X1. They interact.
It's slower, so after some time it doesn't see.
Well, but they interact.
Okay.
Exactly, they are not the
I
same.
need to understand first.
Well, yeah, they interacted for a random number of flips and random time, and yeah. Okay, so why is the symmetry nice? Is because when you consider multiple particles, multiple speeds, then by the same reasoning you can say that, well, if you start all the particles clumped together initially, then particle number n depends on the parameters b1 up to bn in a symmetric way. And because of the symmetry, you can say, well, now I don't have to deal with arbitrary functions of b1, bn, but actually the distribution will be expressed in terms of symmetric functions of.
Can I ask one question because I forgot otherwise? You jump only on one step, yes?
Only on one step.
Do you consider the model when you jump on the many steps and this number of steps depends on the number of the cars on the left side of the... So this is typical fluid dynamics problems.
Maybe. Let's talk later.
Okay.
Yeah.
Because otherwise I can forget.
Maybe. As long as it's integrable, I'm considering it. So when you have something depending on many parameters in a symmetric way, and all the distribution, all the probabilities, all the events depending on the first few particles, or all the events depending on particle xn will be symmetric in B1 up to Bn, so you can try to write them down in terms of symmetric polynomials. So this is somewhat a classical story that I'm not going to discuss in great detail, but symmetric polynomials appear in many different contexts, including combinatorics and representation theory and geometry, and then what we learn about symmetric functions we can then apply to probabilities. So in the case of this particle system, all these probabilities of xn, the distribution of xn is expressed in terms of a Schur measure where B1 up to Bn are going to be the parameters of the Schur polynomials that are going to be determining your distribution. Some of that structure you saw this morning in the talk by Filippo in a more complicated story. But the symmetry was exactly the same symmetry that I'm talking about. But let's put on the probabilist hat and say, well, what if I have a symmetry dependence on B1 up to Bn? What if I take two different systems, one with parameters B1 up to Bn, and the other system when I swap the parameter Bn and Bn minus 1? What happens with these two systems? These are two different systems. I can run them independently. But because of the symmetry, when we do the swap, then the trajectories of almost every particle in the system doesn't change in distribution, like I explained with tractors. So the only trajectory, the only particle that sees the swap is the xn minus 1. So as a probabilist, we have two systems where a lot of things are the same, which means that we should be able to couple them by changing only xn minus 1. So a coupling means that I take a random evolution of one picture, of one particle system, then I do some, based on what I see here, then I do something to the trajectory of xn minus 1, and then I get the evolution of the other system. So exactly what I do is how it looks like is what we figured out with axial science, is that basically, so suppose that this is xn minus 1, and you basically can rebuild the trajectory. So maybe you can start at some terminal time, and then you can actually kind of rebuild the trajectory. So from here, based on these three locations, you randomly move this particle here, and then you build a new trajectory as a random walk in the chamber determined by the other two. And then this is how you draw a different trajectory of the new system with the swapped parameters. So there is a coupling there are many couplings, and they are very explicit that you can map one system to the other. So where does this come from, and how to generalize this? Especially, I don't like this part where you have to start all the particles in the same in a cluster together. So how to generalize that? Well, the Yang-Baxter equation actually tells me how to do this, and let's go back to our two cars, and let's consider the case when they don't start as immediate neighbors. When they don't start as immediate neighbors, then you can see that the back car has a very different behavior. Okay, so here there is a macroscopic. I mean, if this is a large distance, then macroscopically this just doesn't do anything similar to a simple random walk like x2. So what happens is that you can actually forget the middle system and instead take the system where the slow car is in front, but the distance between these two things is random based on this distance. So you take the left system where the fast car is in front, look at where they start, then you flip a coin, or maybe do something kind of random. Take a random geometric variable and take a minimum. So you take a random geometric variable, and so this is G, provided that G, a random independent geometric variable, doesn't shoot over x naught. If G is bigger than the distance, then x naught stays in place. And with this randomization, the trajectory of the second particle is the same in distribution. So again, so we kind of restore. the order, we restored the symmetry. Now that's a new statement, right? It's really bizarre that nobody ever considered this, but it's a simple consequence of the Yang-Baxter equation. So we don't just prove one exercise, but we have a systematic theory of how to get statements like that, and what applications can we get from them. So nobody introduced Yang-Baxter equation that much. So maybe Filippo was, yeah, but you were using it in the background. So what I'm going to use is I'm going to use the Yang-Baxter equation to prove the previous statement by saying that, well, if we look at just one single time moment, and suppose that we know the distance g between the particles and at time t minus 1, and we know what the first particle did, then we encode the distance as a kind of a, so we take, so this is the top row is all possible combinations of motion of two particles, and then the second row is 4 types of vertices that I'm going to put in my vertex model, and I encode the initial distance as a left number, so it's always g, and I encode the jump or no jump of the first particle as this number 0, and the first two things, and 1 in the second two vertices. And so based on what you see, incoming number on the top and incoming number on the left, you actually then make a random choice to put 0 or 1 on the bottom, and these 4 numbers are probabilities based on A2. So here my first particle has speed A1. It did something, and I condition on that motion, and then I decide what the second particle does. So then the decision for the second particle is equivalent to having a stochastic vertex operation. Okay, so but now if I put, right, is that reasonably clear? This is a bijective encoding of the dynamics. So the whole trajectory of two particles can be encoded by two rows. Here I need to put infinity, which is the distance between the first particle and plus infinity. And here I need to put, this initial distance g of 0, and then these two vertices are going to be taken care of the evolution. So there is the Yang-Baxter equation. If I put two vertices, one on top of the other, and I put A1, A2 parameters one side, and then A2, A1 parameters swapped on the other side, then there exists a set of cross weights, phi, which is corresponding to geometric jumps, such that there is this Yang-Baxter equation, which means that if I fix the incoming numbers I1, I2, I3, then the joint distribution of G1, G2, G3 here and on the right and on the left are going to be the same. A1 and A2 are parameters that encode my speeds of the particles. So A2 is always less than A1. It's the speed of the tractor. All right. So this this Yang-Baxter equation tells me that if I take an evolution of a particle system, I attach a cross, because the cross is stochastic. Attaching the cross doesn't do anything to the evolution here, doesn't change the partition function. And now I move it to the left, and it's going to be this picture where here the boundary conditions have to be the same. And so this cross now is applied to the initial configuration. It means that you take the initial distance, and then you make a random geometric jump out of it. That's what this really does. So then you get the same. From the commutation of these two operations, it's a quasi-commutation of these two operations. You get immediately the statement about this symmetry with randomized initial condition. So let me discuss a couple of applications of this. And so the first application is the following. So now there are less trivial probability applications that follow from this argument. So suppose that again, going back to two cars, suppose that I have two cars. The second one is in the back, is slow, and my initial distance is very large. What does it mean is that really there is no influence. Like I can set the distance to go to infinity. There is no influence. So the second car is doing a simple random walk with a slower speed. Okay, but now because of my identity, I have this statement that if I take the first particle, jump it down, and the distance between them is going to be a random geometric variable, then what you see is that the first car now is slow and is doing a simple random walk with a slower speed a2, just because it's the first particle. But now the second trajectory didn't change, so the second trajectory also does a simple random walk with a slower speed, even though it has nominal speed a1. Which means that if you start two particles, one is doing a simple random walk, but the distance initially was geometric, then the second one will also do a random walk. Now that is a Burke theorem. That is what people call Burke's theorem for the particle systems. And then you can iterate this and say, well, but what if I iterate the statement? Then I can generate a whole series of independent geometric distances. And so the particle configuration will be II Bernoulli, because there are geometric distances between particles of this density. And so if I start, the fast particles evolving in a IID Bernoulli environment, then that would be each particle marginally does a simple random walk, and collectively they have a they evolve in stationarity. So it's how we construct a stationary distribution for TASEP by just doing little cross manipulations in Yang-Baxter. So going back, same thing, but what happens with crosses in the previous picture? So I take the slow A2 slow line. I put infinity here. So it's infinity as opposed to these pictures. Infinity now in the second direction. If infinity is in the second, if infinity number of arrows is coming here, then what this yellow line does is actually it deposits IID geometric random distances here. So G1, G2, G3, G4 are IID geometric A2 over A1, and so this is the initial condition for my TASEP, such that it's going to be stationary. So you can take vertex models and combine them to build a stationary distribution, right? So that's the first application. Second application is when you actually take maybe a flat initial condition. So you take flat initial condition, meaning that you have a particle hole, particle hole, particle hole. And suppose that every blue particle has speed 1, every orange particle, single orange particle has speed less than 1. Then you can exchange, and then you have the statement that this particle, the distribution of this trajectory is going to be the same as the distribution of this trajectory. But now what happens is that we know from TASEP that if you take, well, suppose that we are in continuous time. So if we take the flat initial condition, then this whole collective of blue particles has macroscopic speed 1/2. So it's kind of like a traffic jam sort of, but it has macroscopic, sorry, 1/2 or 1/4. Yes. Well, so we know the macroscopic speed, and now we can take A1. I think it's 1/2, and depending on the value of A2, you would take. You would see either that this orange particle didn't catch up with these guys, and so it does a simple random walk, or maybe it catches up and has some kind of a shock interaction with this collective of particles. So at the Yang-Baxter level, this is what happens, and depending on A2, the initial distribution, the randomized initial condition, will look very differently. So either all blue particles will be like very close here, or maybe they will roughly stay in the same places. There is a simple phase transition. Okay, so that's another application. So there is a third application. You can just again take the same situation, but now let's take my speeds to be a geometric sequence 1 r squared, r cubed, r fourth. And so the first particle is going to be the fastest one. And then I'm going to exchange them. I'm going to exchange the speed one, the parameter 1. I'm going to exchange with the second one and the third one and so on, and let one go to infinity. Let the speed one go to infinity and disappear there. And so I will get a relation between my particle system with parameters 1, r squared, and so on, and another particle system with parameters r squared, and so on. So all the parameters, all the speeds are multiplied by some number less than 1. So I get kind of a relation between the same system altogether, and you can make this work and get a relation of this sort. So if I have a T, which is my TASEP semigroup, and another instance of the TASEP semigroup at the earlier time, then you get some kind of a commutation relation for one Markov transition operator in TASEP during time t, and you can actually differentiate this relation and get some kind of a lax form of an equation between the TASEP semigroup and another particle system that jumps back. So here's what this relation reads. This is the first result I wanted to discuss. Like the first really non-trivial consequence of this cross manipulation is this equation. I don't. I'll show you one computation with this equation that is going to be maybe tell you that it's worth something. So what is T of t? T of t is the Markov transition semigroup of a process that is my TASEP. It runs for time t, and B is the infinitesimal generator of another process that acts on particle configurations by the following procedure. So each particle now under B will jump back according to a random distance. And the further particle is from the right-hand side, the faster it will jump back. And so when a particle jumps, it randomly uniformly selects the place to land inside this gap. And the rate of the jump of the particle is going to be equal to the size of the gap times the particle's number. So is that fluid dynamics enough?
But super nonlinear system, when you jump, depends on the configuration of the particle.
It does.
Not random selection of the distance. It should be somehow deterministically depend on the number of particles that lie near this particle which jumps. So this is super nonlinear.
This is slightly different, but
because this looks like a combination of random walks with different jumps, something like that.
Probably.
In fluid dynamics, this is open problems that related to Navier-Stokes equation.
Okay. This is probably
anyway,
might not be related.
This problem is also very interesting.
Okay. So here's this lax equation, and let me just show you a little bit of computation that you just start with this lax equation and try to get some information about my TASEP out of it. So suppose that right. So if you write it in probabilistic language, then you get a differential equation for time evolution of any function of the whole particle configuration. So if I pick a function in a smart way, and if I start from the step initial condition, then if I start from the step initial condition, then one of these terms disappears because B only moves particles back, and then if Y is my step, then there is no moving back. So this is killed. Now you only have the second term, and if I take my function to be just some other like one-dimensional function of a height function at a point, then I get the following equation for the G of H evolution, where it basically has a discrete derivative of G, and it also has some kind of an observable. So this is a global observable. This is a global G depending on the height function times something that you see around you. Only this rxt is the number of holes around x, basically, to the left of x, to the next particle. And so if you believe in niceness of limits, then these two things will be independent in the limit or uncorrelated in the limit. So you get this product, and from this product you immediately get time evolution for g of h, which confirms the known TASEP, limiting densities and all that. So of course, this is an ansatz that you don't know this initially, but they are independent in the limit, and you get the same result. So now, because I started with the Yang-Baxter equation, I don't have to limit myself to TASEP. Actually, you can insert q everywhere, and you can have particles jumping not just with rate 1, but maybe with rate 1 minus q to the distance to the next particle. That's the q TASEP. And the Yang-Baxter equation works, and you can have a local observable, which is going to be some q observable. So it's not as easy, but it's not hard either. And then you can confirm the limiting density for q TASEP as well. All right, so that's the third application of this simple idea. Do you have any questions before I go to the next part? And if you have no questions, then it's also a good time to wake up for the next part. Okay, so I was talking about particle systems where every particle has its own speed, but all the particles were kind of indistinguishable otherwise. Now, you can also introduce colors, and you can also say that every particle has its own type, and then when the two particles meet and decide who jumps first, then they compare the types. So this is called second-class particles. So you take a first-class passenger, second-class passenger, they compare the tickets, and they know who goes first. So this is what happens with color systems. And there are many different integrable stochastic systems. This is just a part of the scheme. And then there is this one model that is the simplest looking, maybe, well, apart from TASEP. And by limits and degenerations, you can get other systems out of it. And what I was talking about in the first part works for TASEP and its Q deformation. But there is also ASEP, where particles just jump left and right. And they jump right with rate 1, they jump left with rate q or t. And what I said doesn't quite work for ASEP, because if you take ASEP with particle speeds that depend on the particle, then ASEP stops being integrable. There is no symmetry. If you try to compute the same distributions, they now fail to be symmetric in my variables, even from the step densely packed initial configuration. But there are some facts for ASEP that I can still salvage, and we have to go back to the drawing board and have to start with graphic manipulations at the very top level. And what we can salvage is it's what we did with Amol Agarwal and Matthew Nicoletti last year, is to construct stationary measures for these particle systems, starting from the same idea. So you have the stochastic 6-vertex model, which I'm going to define in a second, and then that thing also satisfies the Yang-Baxter equation. Then in the Yang-Baxter equation, you put infinitely many arrows. Then the Yang-Baxter equation produces a stationary measure for you. And you can also do this in color, and you can also do this in other geometries. So we did it for the system on the ring. And that's going to be my second main result that I'm going to formulate in the end. So let's go back to graphic manipulation. So here's the stochastic 6-vertex model. This is a system that lives in the quadrant. It has some boundary conditions, and the configurations in the stochastic 6-vertex model are precisely osculating paths. You can have one of the 6 configurations. It's stochastic in the sense that every vertex becomes a coin flipping mechanism. It looks at who comes in, and then depending on who comes in, if an arrow comes in from the left or from the bottom, then it flips a coin and decides what the arrow does next. So oops. So for instance, this vertex decided the arrow goes through. This vertex decides the arrow turns. And this vertex doesn't have any decisions because it has one arrow incoming from the left, one arrow incoming from the bottom. And in the stochastic six-vertex model, I'm allowing at most one arrow per edge. So there is no choice. This with probability 1, this happens. And this is that vertex. So I have parameters delta 1 and delta 2, which tell me which completely determine the stochastic six-vertex model. And on top, there are vertex types A1, A2, B1, B2, C1, C2. So if AIs and BIs and CIs are all the same and equal to 1, then you get this delta 1/2 alternating sign matrix model. So it's just a different specialization of the general six-vertex model. And so what is stationarity here? Stationarity for the stochastic six-vertex model means that just I take some initial data along the boundary, and then I run my six-vertex model. And stationarity means that the joint distribution of all the arrows and holes here should be the same as the joint distribution of all the arrows and holes if I shift my quadrant. So that's the stationarity. And so we want stationary measures. Why is that? Well, because if you take delta 1 and delta 2 going to 0, then one of the reasons why we study stochastic six-vertex model is that you can take a limit and get TASEP out of it by taking just limit delta 1 and delta 2 going to 0. So delta 1 and delta 2 are probabilities to go straight. So if the probability to go straight vanishes, then every path wants to do a staircase motion. If it does a staircase motion, if I let my time be diagonal and space be orthogonal to it, then every staircase looks like a particle that's sitting there for a long time, but then in a Poisson limit, as time goes to infinity, proportionally to delta 1, delta 2, a staircase might move to the left or to the right, and there are two different rates, 1 and q, that govern the motion of staircases. So in stochastic six-vertex model is going to converge to ASEP, and then when I set q to 0, then I get TASEP back. Okay, that is clear, right? So that's why we can study stochastic six-vertex model, understand stationarity question there, and take a limit to ASEP. By the way, stationarity for like ASEP and TASEP in the absence of colors is very easy. The stationary measures for this particle system are precisely IID Bernoulli configurations. I mean, extreme stationary measures, which are translation invariant, are precisely the IID Bernoulli. So there is no we really need this theory in the Yang-Baxter equation to be able to get colored statements. Then if you have colors in particle systems, then stationary measure is becoming much more complicated. But even the single color for the stochastic six-vertex model, you actually need two different densities of the Bernoullis on the either sides because there is this computation that you can do, and it gives you a linear equation for it gives you an equation between density in the rho h and rho v. So what is this computation? How to understand stationary measures here? Well, suppose that I'm looking at a single vertex, and suppose that I want the probability that I have an arrow sticking up and nothing sticking to the right. Then I want it to be stationary, so I want the probability of that event to be rho v times 1 minus rho h. But then I have to, this event has to be a sum of two events, given that given that I know my configuration before, which happens with these probabilities, times the delta or 1 minus delta probability for the motion of the arrow that this vertex does. So this equation is equivalent to this under parameterization by u, and it doesn't depend on q, which is helpful. There is a second equation. So this is an equation for arrow sticking up. There is a second equation for arrow sticking to the right. It turns out these two equations are equivalent and give you one parameter family of solutions. That is integrability. Well, two arbitrary equations don't necessarily want to be equivalent to each other, right? But here somehow these two equations are giving you the one parameter family. So, which means that stationary measures for the stochastic six-vertex model are obtained in the following way. You just take a Bernoulli of some density that you like here, and then here you need to take a Bernoulli with a corresponding density depending on that. And then you run the stochastic six-vertex model, you get stationary distribution. So this is the Burke property of the stochastic six-vertex model. But we have the Yang-Baxter equation, so let me tell you how to get the same using the Yang-Baxter equation. So the Yang-Baxter equation for the stochastic six-vertex model, well, originally, if you write it down, then all the three weights here will be stochastic six-vertex, meaning they allow only at most one arrow per edge. So that doesn't work because I want to put infinities everywhere, right? So if I want to put infinity not everywhere. I want to put infinity on one line that crosses my Yang-Baxter picture. So the way out is to go to some procedure called fusion that builds new solutions to the Yang-Baxter equation out of the old ones, and one can check that if you allow fat line to be vertical and you get stochastic weights which depend on parameter x and parameter q in this way, then then for these weights you have this Yang-Baxter equation. So this topologically this picture is the same as this picture, except that in one line I allow arbitrary many arrows. And this already implies the stationarity in Burke because if I let g, the number of arrows along the fat line, to be infinite, then these weights stop depending on the input. So the input will be ignored, right? It's q to the g goes to 0. So this weight 1 over 1 plus x is the probability to deposit nothing. X over 1 plus x is the probability to deposit an arrow. So this fat vertex becomes a mechanism for depositing IID Bernoullis. And the Yang-Baxter equation here tells me exactly that if I deposit Bernoullis with parameter x and parameter y, and then hit this thing with the vertex model, then the joint distribution of the output is going to be the same as if I move the fat line, ignore the vertex, and just deposit IID, things in the first place. So that's stationarity. Okay. So if you compute the relations between the parameters, you get exactly the same equation from the Yang-Baxter equation. Okay. So there are two more things I want to show before formulating the result, and the second thing is that right. So this is how. Well, even before that, I need to explain that. Of course, you can iterate this procedure. You can take the initial conditions and you can flip corners one by one. Okay. So the next thing is I want to add colors, and I can just do it because I have 5 minutes left. I can just do it very quickly. So there are more formulas, but let's go here. So conceptually, if my vertex model now has colors, which means that every arrow has its own color, then to construct a stationary measure, I need some random combination of colors initially in the boundary of the quadrant. So to have that, I would be able to deposit a random combination of colors. So these color configurations will no longer be IID Bernoullis, but rather, suppose I have 3 colors. Then I need 3 fat lines going along the boundary. Each fat line will deposit a new color of its own. So this purple line will deposit the first color, pink line will deposit the second color, green line will deposit the third color. But then when they deposit colors, then these colors will go through the next line and interact with it and do something random out of it. So here's an example of how you can generate an initial condition. So the first one is the outermost fat line that deposits color number 3. Then color number 3 enters the second line, the color -2 line, moves a little bit and then sticks out, and then you get more colors coming in, and this produces a stationary distribution for you. Now it's more complicated. It has dependence of colors. So if you only have 2 colors, then what you're looking for is the following configuration. So you have an infinite line, and you have 3 types of objects on the infinite line: holes, particles, and say pink particles and green particles. And so pink particles will have IID Bernoulli joint distribution if you just look at the pink particles. If you look at the combined pink and green and forget about the color, and these guys also have an IID Bernoulli of a bigger density, but the green particles themselves don't have an IID Bernoulli. Well, I mean, that's impossible. So that's what kind of a distribution you get in the case of 2 colors. And you can deposit this distribution, and then you can check that distribution is stationary by flipping each fat line one by one. What do you need for that? You need the weights for the for the fat vertices. So the weights for the fat vertices are exactly what I skipped. Okay, so I guess I was rotating. Sorry. So the weights for the fat vertices in colored situation are some things that I skipped, and these are some functions depending on, well, this vertical line is fat, and these weights were obtained by fusion. So you can find these in a paper by Alexei Borodin and Michael Wheeler, based on SLN Vertex models. And so for each fat line of a given color, we need to take that color and send the number of arrows of that color to infinity. Okay, so this is how you can construct stationary distribution for ASEP on the for a stochastic 6-vertex model on the quadrant. You can also construct stationary distribution on the ring by taking the same fat lines and then taking your vertex model that used to be a grid and wrapping it around the cylinder. Once you wrap it around and take the same limit to the ASEP, then what particles do is each particle makes a staircase motion. But since I wrapped my grid around the cylinder in this way, then the staircase motion would actually correspond to a particle staying in place, and then occasionally particles jump up and down. So for this system, you can construct stationary distribution, and the Yang-Baxter equation allows you to prove stationarity because you can just take the crosses and then flip them, and move them all the way to the left before my fat lines. And remember that fat lines don't remember the initial conditions, so that's how you can prove the stationarity. Okay, so I guess that was too fast, but let me just show you how the stationary distribution for multi-species ASEP looks like. So this is these are weights that on the ring, when you have only three particles in one hole on the ring of size 4, these are the stationary probabilities of the configurations that you can find in the paper by James Martin, who studied this. And so these weights, by Yang-Baxter equation, they can be realized as partition functions of vertex models with fat lines. Okay, so that's the second result I wanted to talk about. So, right, that was very simple, right? You just do a little bit of graphic manipulations, and you get non-trivial probabilistic consequences. That's the bottom line. And yeah, so let me let me emphasize that everything just relies on creative placement of crosses and moving the crosses and interpreting what Yang-Baxter equation tells you in the probabilistic language. And this gives you some kind of relations for TASEP, like Luck's equation. You can construct stationary distributions for particle systems by just modeling them as vertex models by creative placement of Yang-Baxter crosses. All right, do you have any questions?